This is section 7.4, and we're going to take a look at our next technique of integration. It's a technique called trig substitutions, and as per its name, we will be using a bunch of trig again. We'll be using this technique to evaluate integrals that have one of these three radicals in them, the form square root a squared minus u squared, or the square root of a squared plus u squared, or the square root of u squared minus a squared. The little chart down here helps us figure out what to do when. And what I'd really like you to concentrate on is right in here. Depending on which of these forms we have, what the radicand is, we're going to make a different substitution each time. Now, they do give us some information about domain issues. I'm not going to spend a lot of time with that. The useful identities, those are going to come right out in the wash as we do the problems. So mostly I want you to concentrate on this for our purposes here today. The bottom talks a little bit about drawing triangles. We'll get to that when we do our first example. So I'm going to concentrate again on this. You'll see this come into play as we do some of the problems. All right, so in our first example, I can see that under my radical, I've got a constant minus the x squared. So that would be this form right here, a squared minus x squared. And in our particular case, the a value is 4. So the suggestion here is that we should make the substitution x equals our a, 4, times the sine of theta. So let's do that. We're going to let x equal a sine theta. Notice this is quite a different type of substitution than what you're used to. Instead of letting u be something involving the x's, we're letting x itself equal something. Okay. Oops, and I said 4, I wrote a. All right, I need dx for this problem, so let's go ahead and do the derivative. That would be 4 cosine theta, d theta, right, I really did dx d theta, just move the d theta over. And so with that, I'm going to go ahead and substitute into my integral. The top dx becomes 4 cos theta d theta. And on the bottom, I've got x squared. That would be 16 sine squared theta, just squaring my x. And then under the radical, 16 minus that same x squared. All right, next thing we're going to do is a bit of algebra and trig to simplify our integral. I know it kind of looks like we made it worse, but with a little bit of algebra and trig, I think we can see that it's actually better for us now. Not much I can do in the numerator, so I'll just recopy that. But under that radical, if I factor out the 16, I'll have 1 minus sine squared theta. And remember, 1 minus sine squared theta, that's just one of our nice trig identities. That's cos squared theta. So underneath my square root, I've actually got 16 cos squared theta. Now notice, that's 4 cos theta, and I've got a 4 cos theta on the top. So actually, I can divide those out right now, get rid of them. This is what I've got left. I need to be able to integrate that, but I think I'm in luck. I could take that 16 in the denominator and just pull that out, 1/16. And then 1 over sine is cosecant. So that's actually cosecant squared theta. D theta. And lucky for us, cosecant squared is one of the few trig integrals that we know how to do directly. It is negative cotangent. So I'd have 1/16 times negative cotangent theta plus c. All right, that's great. The integral is actually done. There's no more integration in here. Eventually, I'll pull the negative out in front. But before I do that, I'm going to say there's a little bit of a strange feeling about this answer, because the original problem was in terms of x, and my answer right now is in terms of theta, which doesn't make a whole lot of sense. So let's see if we can go back and put our answer in terms of x. This is where the construction of the triangles comes into play. So over here, I'm going to rewrite this x equals statement as sine theta equals x over 4. Just a reminder, sine is opposite over hypotenuse. So if I were to draw myself a little triangle, opposite side needs to be x, hypotenuse needs to be 4, and then we could just do a little Pythagorean theorem here. And find that a would be 16 minus the x squared, square root of that. I'm now going to read the results here right off that triangle. I would have a negative 1/16 times, let's see, tangent is opposite over adjacent. So cotangent would be adjacent over opposite. That would be adjacent here over opposite there. And I can leave my final answer just like that, or I could make the 16x in the denominator. It doesn't matter. I'm just going to leave it like that. And there we go. All right, let's try a couple more like this. In example 2, we have the square root of dx over the square root of 9x squared plus 4. Now there's a couple of different things that I need to deal with here. First of all, you'll notice that every single one of our substitutions depends on having just a plain x with no multiplier on it. So I'm going to have to deal with that multiplier of 9. In order to do that, my first step is going to be to factor out the 9. Like so. And then the square root of 9 is 3, so I can just pull that out as a 1/3. All right, now I'm in good shape, and I've got the x squared plus a squared form. This form right here, x squared plus a squared. So I'm going to notice that in this particular case, that's a squared. So a would be the square root of that. A would be 2/3. And according to my little cheat sheet here, I then want to let x equal 2/3 tangent theta. All right, that means that dx would be 2/3 secant squared theta, d theta, and that's what I'm going to plug in here into my integral. So there's the dx. And then under the radical, I have x squared. That would be 4/9 tangent squared theta plus the 4/9. All right. Once again, it kind of looks midway that I've made things worse, but I think we'll be able to work it back around here to make things look a little better. First thing I'm going to do in that denominator is factor out the 4/9. so. And there's another familiar Pythagorean identity. Tangent squared theta plus 1, that's just secant squared theta. So in fact, what I have here in my denominator is the square root of 4/9, which would be 2/3, and then the square root of secant squared theta, would just secant theta. I can divide out those 2/3 and one of the secant thetas, and I just end up with 1/3 integral of secant theta d theta. That one is on my sheet. It's the natural log of, in our case, secant theta plus tangent theta. And then I'm back to that same issue again. I know that I don't really want thetas in my answer. This problem was given in terms of x. So let's go back and think about our triangle. I can see here that if I were to solve for tangent theta, I'd have 3x over 2. And that's going to be the opposite over adjacent. So if I were to draw my triangle, opposite would be 3x, adjacent would be 2. Okay. Pythagorean theorem, that's just c squared, or c rather. So a squared plus b squared would be 4 plus 9x squared, that would be c squared, and if I take the square root, there's my c. So I've got 1/3 times the natural log of secant theta. Let's see, that's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so this would be hypotenuse over adjacent. Hypotenuse, square root of 4 plus 9x squared over adjacent 2. Plus tangent theta, opposite over adjacent, 3x over 2. And then my plus c. All right, so again, bit of work, but we can sort of see the technique that's happening here. I want to do one more that's, we're basically just going to do in this straightforward way. And then I'm going to show you a problem or two where we can kind of get a bit creative. I'm going to show you some multiple solutions, which I think are rather interesting. Here we go. Example 3. We've got x squared over the square root of 9 minus x squared as our integrand. And if I go back to my list again, it looks like we're kind of back to this one again. That 9 minus x squared is this form with an a of 3. So I'm going to want to let x be 3 sine theta. Dx then will be 3 cosine theta. D theta. And substituting everything into my integral, I have x squared, so 9 sine squared theta times dx, 3 cosine theta, d theta, over the square root of 9 minus my x squared, which is 9 sine squared theta. All right, the numerator is 27 sine squared theta cos theta d theta. And in the denominator, when I factor out the 9, I have 1 minus sine squared theta. That, of course, is really cos squared theta. So in the denominator, square root of 9 is 3. Square root of cos squared theta is cos theta. And it looks like I can just divide out the cosine thetas. And 3 goes into 27 9 times. So I end up with the integral of, I'm going to pull the 9 out, and then I've just got sine squared theta d theta. All right, that's not on our list, and there's no good trig identity to make it be on our list, so we're going to have to go back to what we learned in the last section here. I've got an even power of sine, so I'm going to use the power reducing formula. Power reducing identity. To rewrite that sine squared theta as 1 minus cosine 2 theta over 2 d theta. I'm going to pull the 2 out, so that's 9 halves. And then the integral of 1 d theta is theta minus the integral of cos 2 theta would be sine 2 theta. And notice there's a little bit of a u substitution there. U would be 2 theta, which is going to cause me to have a 1/2 out here. All right, my integral is basically done. I am ready to just go ahead and go back and get the thetas out of there. So let's draw our triangle. Sine theta would be x over 3. And that's opposite over hypotenuse. And you can write out your Pythagorean theorem if you need to, but I imagine probably a lot of you are doing them in your heads at this point. That would be 9 minus x squared. The square root of that would be down here. So I've got 9 halves times theta itself. Now, that's kind of an interesting one. How do I write theta based on any of the information that I have? I'm not going to actually get it off the triangle. I'm actually going to get it off of this equation. Since sine theta is x over 3, theta would be the arc sine of x over 3. And then I have minus 1/2. And then I've got a sine 2 theta. Well, let's see, that's really 2 sine theta cos theta if I use the trig identity. So 2, and those should cancel out. I probably could have done that in the previous stuff, but I didn't catch it in time, so we'll do it next. Sine theta, which is x over 3, cosine theta, which is the square root of 9 minus x squared over 3. All right, almost there. We've got 9 halves, arc sine, x over 3, minus, and I'm going to write that fraction as x, square root 9 minus x squared, all over 9. Plus my constant of integration. Okay, so again, couple of different techniques in this one. Never surprised when old techniques crop up in the middle of new problems, right? But there we go. All right, the next two problems actually are somewhat similar in that they can be done multiple ways, and I probably should have only put one of them in, so I'm going to go ahead and I'm going to choose to do example 4. 5 is very, very similar, so in terms of just being able to be done multiple ways. So I'm going to go ahead and do 4 with you. You'll probably end up needing more space, so feel free to use the page that 5 is on. We will not do 5, at least not together. All right. Looking at example 4, my first thought is it doesn't quite fit the format, right? The format that we've been wanting here has been something that looks like one of these. And with that X there, it doesn't match these at all. So once again, I'm going to call in an old trick that we've already learned. When you have a denominator like this, try completing the square. You may even remember this because we've seen it before. I'm going to factor out the negative sign and write this as x squared minus 2x, or something very similar anyway we've seen before. In order to complete the square, I would have to add 1 in here. But because of the minus out here, that's really a minus 1. To compensate, I'll add 1 outside of the parentheses. So I've actually got, I'm going to put the 1 first, subtract, and that's x minus 1 squared. Okay. Not too bad. That's a little unwieldy, and you may remember when we did these completing the square problems before, we usually let u be whatever this was. So we're going to go ahead and do that. I'm going to let u be x minus 1. So du is just equal to dx. So I now have du over the square root of 1 minus u squared. All right, from there, I'm going to say there are 2 ways we could go. We can actually just look this answer up. That's the simplest way, and I'm going to do that first. But then I'm also going to say, well, with our new techniques of trig substitutions, this is a good match for that, right? So we should be able to do it using a trig substitution as well. And I'd like to look at those 2 different techniques and compare them. First of all, let's do the easy one. We can just look this up. It's right here. My a would be 1. X is actually u. So just using my table of integrals, I should get the inverse or arc sine of u over 1 plus c, giving me a final answer of arc sine. U is actually x minus 1 plus c. All right, let's see what would happen if instead we used our trig substitutions from here. We would certainly hope we'd get the same answer. Let's try it out. I'm going to go ahead and I'm actually going to start right from here. And instead of looking it up in a table of integrals, instead I'm going to use my new trig substitution technique. So we're starting from that same point. The previous step, the completing the square step, we certainly don't have to repeat. All right, so again, looking at my options here, I'd be in the a squared minus x squared case. In our case, a would be 1 and x would be u. So I'd want to let u be 1 sine theta. Let's do that. So du is just 1, or the derivative here, cosine theta. D theta. And my integral becomes the du cos theta d theta over the square root of 1 minus u squared, which is sine squared theta. There's that familiar form of that Pythagorean identity again. What's under that radical is actually just cos squared theta. And since the cos squared theta square root is just cosine theta, I can divide those out. And I really just end up with the integral of 1 d theta, which would be theta plus c. But what's theta? Well, theta would be the arc sine of u. And then going back, u is x minus 1. So there we got the exact same answer again. All right. So if you do recognize something as being part of a table, hey, great, more power to you. It's often the fastest way to go. But if not, the trig substitution will still get you to the same place. I did want to mention one more thing about this. Something that actually came up in a class of mine a year or two ago. A student asked me about an alternative possible technique, and it was really clever. And ever since, I've been kind of using it as an example because it illustrates something that we have not seen yet, but it's kind of important. So I'm going to go ahead and I'm going to redo the same problem one more time. And this time, I'm not going to complete the square. I'm going to use a completely different method. So we're going to go ahead and back to example 4 again. Alternate method. And I have to credit my very creative and inventive student Dale from a couple years back for asking me this question and saying, hey, couldn't you do this? And I thought, wow, that was really, really clever. Here's what he did. He said, let's factor the denominator. And he actually factored the square root of x right out of there. So notice with both of those being square roots, if I distributed, I'd have 2x minus x squared back under the radical. And then he chose to let u be the square root of x. It's just a standard substitution, not a trig substitution. So du is 1/2 x to the negative 1/2 dx. And 2 du would be 1 over the square root of x for that x to the negative 1/2 dx. So notice that is right there. And I can substitute 2 du for all of that. So we're going to have 2 du over the square root of 2 minus x, but I don't want an x in here, I want u's. Notice that x would just be u squared. All right, so we're good to go so far. Now, at this point, he did go back to the idea from the table of the arc sine. So we're going to go here and say, if we let a be the square root of 2 and x be u, we would have, so you can see everything on the screen here. I'm going to pull this 2 out in front. And then this, again, a is the square root of 2, x is u, so I'd have inverse or arc sine of u over the square root of 2. Plus c. So that would be 2 arc sine of my u, which is the square root of x, over the square root of 2, plus c. All right, pretty clever. It involved really seeing through this problem to see that that du was going to be so handy right there. Now, here's the reason why I like to run this through. Yeah, this is a perfectly legitimate way to do this problem. In fact, take a quick look and make sure. I don't think we've made any mistakes. I think everything we've done is perfectly okay. But you might be asking, wait a minute, didn't we get a different answer before? In fact, we did, right? Before we got this answer. And I did it 2 different ways and got the same answer, so that had to be right. And now I've done it a 3rd way and gotten a very different looking answer. The secret to this is actually in the plus c. I'm going to graph both of those answers. In fact, I think I already have. They're right here. Top one is the first answer we got, the arc sine or inverse sine of x minus 1. And down here is the second answer, the one we just got, 2 times the arc sine of the square root of x over 2. Going to the graph, look what happens. Would you agree with me that those look like exactly the same graph, just shifted vertically? And what is a vertical shift? Isn't adding a different constant what causes a graph to move up or down? So these really are, even though they look very different, these really are the same function, differing only by a constant. And that's because that plus c, the constant of integration, can be different for the 2 problems. What we're seeing is one graph that looked kind of like this, and another graph that looked kind of like this. But they consistently differed by just a constant. So when you're doing these, don't be surprised if you do a problem and someone else does the same problem by a different method. You get 2 different looking answers. Doesn't necessarily mean one's right and one's wrong. They could actually be the same, or at least the same up to that constant of integration. All right, that brings us to the end of section 7.4.